Hi, today we will talk about our process of developing an image analysis tool that could ultimately be used to study the effects of zero and low gravity effects on muscles. Maintaining human health and performance in space is a difficult task, as especially muscle atrophy is a constant problem in microgravity environments. In order to find the most efficient countermeasures for this problem, extensive research about muscles and therefore standardized diagnostic tools for the clinical examination of muscles are needed. In our project, we tried to develop such a tool to detect muscle fascia. For this, we used ultrasound images of gastrocnemius muscles, which were provided by Professor Dr. Jörn Rittweger and Jule Heyeis from the Institute of Aerospace Medicine at the German Space Agency. And we looked for a way to automatically detect the superficial and deep aponeuroses in these ultrasound images and to annotate them without the need of a professional. The aponeuroses are a type of deep fascia and provide the outer lining of the muscle. Their segmentation is thus a necessary first step in the development of standardized evaluation methods.
In order to get a feeling for the images and quickly finding the challenging areas, we started the edge detection process by applying common image preprocessing filters. A well-known example is the Laplacian edge detection, where the results are shown on the right here. The first step is to blur the image with the Gaussian filter in order to only extract the main features, and then detect edges by using the second derivative Laplacian filter. Other filters that we tried and tested included the Sobel filter and the Canny edge detection algorithm. However, by simply applying the filters and playing around with some parameters, we did not get the results that we expected. So while this was a great method in the beginning to get quick edge detection results, we did not find the quality sufficient to be useful.
To overcome these problems, we have taken another approach. Image segmentation, a deep learning method, was applied. This method assigns a label or a class to every single pixel of the input image, enabling a very detailed partitioning or classification of the image. One of these models is UNAT, which was first introduced in 2015 with the architecture shown in the middle. It was originally created for the application in the biomedical field. The two images on the sides are an example of this classification method. The input image on the left side is a simple preprocessed input of an ultrasound image, and the one on the right side shows the result of the prediction. We aim to find and differentiate between the upper aponeuroses visible as the green line and the lower aponeuroses shown as the red line. Since the lines are usually distinct, the image is more or less similar, and the model seemed to fit the task well, as it was originally designed for biomedical applications. The model reached relatively high scores, visible at the two graphs on the left side. As one metric and as the loss function, categorical cross entropy was used, and another in image segmentation often used metric, the dice score and its progress during the training is shown in the lower graph. These reassuring results are partly due to the aforementioned details, such as the similarity of the image settings, and partly to the method applied called image augmentation. It is usually applied to increase the amount of training data by applying transformations to the images during training. These can be either simple modifications, such as the addition of noise, but can also mean geometric transformations such as rotation or perspective transform. It makes the model more robust, and it is therefore able to perform reliable predictions also in new, noisy, and different data. Since it is applied at each training round, called epoch, the model has seen during the training a slightly different image every single time. An example of the augmented images are shown in the right picture. And finally, here are a few examples shown. It is important to mention that the images presented have never been shown to the model during training.
The final step is to describe the pixel-wise prediction with a continuous differentiable function. The most intuitive type of function at this point is a polynomial. And since the multi-class prediction returns 2 different classes, we can fit 1 polynomial to each class. We found that a function of the 4th degree is sufficient to be a good fit to the prediction data. Now, the description containing the coefficients and the intercept with respect to an image coordinate system can be used to describe the difference between images as a difference of functions. And this could be especially useful for the research of the movement of the fascia at different contraction states.
As a last step in our work, we opted to visualize our results in a website form. To build this website, we used mainly the Dash library from Python. It is a multi-page website with a home page where you will find the main motivation behind our work, and the second page, which is the tool page. Here you will find the tool that will enable you to recognize the Aponeuroses. To use it, you firstly start with selecting your image by simply doing that. And then, after waiting some seconds, the denoted image will be displayed. As shown here, this is the denoted Aponeuroses. You see, quite a simple and efficient website. Finally, this project has enabled us to build an easy, accessible tool that can automatically identify Aponeuroses in ultrasound images and annotate them accordingly. This tool can be used for other research groups as well as for those who study calf muscles. Some of the potential next step for this work is to add features to detect fascia curvatures, fascicles, fascicle curvature, and pennation angles. Here are some sources that we used during our work. And here we come to the end of our presentation. I would like to thank you all for your attention and have a nice day.